Did we actually finish it though?
I thought it was for acquisition.
Yeah, it might be. But you guys, because this, I'm going to tie this together. Can I bore you for a minute? Just revisit it. Because I think, literally speaking, here's my x-axis, here's my y-axis. The graph that curve looks like this. So I think what the question is really asking is the following. Can you and I compute the area beneath the curve as x ranges from 1 on up? Now, I admit it's an unbounded region, but its area might be finite. So, let's play. Dividing this integral. I'm simply going to anti-differentiate what's the Lagrange position and evaluate. So what do you think? What do you mean no, why not? I agree with the answer, by the way.
We can't do that.
Why not?
We can't take the zero.
Because there can't be a zero in the denominator. But
You can't
no,
do
there is
that.
you can do that. Why couldn't you do that?
It's just gonna be
Oh no, you gotta actually change the infinity to t and
Why
for the
do I
limit.
have to?
Well, because you can't just integrate to infinity. You have to do it with a limit.
But it sounds like you're saying something you've heard or something I've said, but why is it the case that you can't do that?
'cause
Oh.
you're never actually gonna.
You're never gonna find an exact value because it just goes on infinitely.
True, Nice. He's saying I can't really divide 1 by infinity. Infinity is not a real number. You know what I was hoping you would say? I was hoping you'd say, by definition, a definite integral with bounds a to b is the limit of a Riemann sum that involves a delta x, where delta x is the length of my interval from a to b divided by n parts, or excuse me, divided n times. And my interval from a to b is actually an interval on the real number line that itself is unbounded. So I can't come up with my delta x using my definition of definite integral. And so I think I am stuck. I think I'm way off. Here's how I'm going to get out of my trap. Before I actually anti-differentiate, I will rethink of this improper integral. It's improper because one of my bounds of integration is not finite. I will interpret this as a limit. I'll make up a letter out of thin air. How about t? As t increases the bound of this particular definite integral. But when you look at what's within the limit, that's a definite integral where t is supposed to represent a finite fixed real number, albeit maybe rather large. But using my definition in Math 30 of my definite integral, now I can deal with the limit of a Riemann sum, because I can compute my b minus a over delta over n, which is my delta x. Now, life's a piece of cake, no tricks. I really do think I can anti-differentiate using a second fundamental theorem of calculus, and coming up with an antiderivative, I'll evaluate it from lower to upper bound of integration. And I think that merely gives me a limit, as t increases with that bound, of my -1 over high bound of integration, minus my -1 over x, evaluate lower bound of integration. And I still do get the number +1. Meaning, of course, the area underneath that curve is indeed finite, specifically is equal to 1. Did I mention going to Lowe's? That I really can go to Lowe's and buy enough paint to paint that region? It's just that when I get home, I'll never be able to paint the entire region, so I can't walk out that far. But I certainly can buy the amount of paint needed to paint that region.
Where do you live?
Close to Lowe's. So, everybody, can we skip number 2? It's the same thing, right?
No.
Yeah, maybe not. If I came in and evaluated this integral, is it 1 over root x? I think the same as this. Now, it's a proper, excuse me, I misspoke. It's improper integral because I really do have one of my bounds of integration, at least one of them, that's not a finite fixed real number. So I'll rewrite as a limit, just like I did in my last example, of this particular integral. And I maintain at this stage of the game, everything's legal for Math 30. When you take a peek at what's above this brace, I will apply the second fundamental theorem. I'll, number 1, anti-differentiate. And and evaluate. But I think that's gonna give me the limit as t plays its game of jeepers, what is that gonna give me? Is that gonna be 2 root t minus 2? So help me with this. When you value this limit, what do you get? I agree. That being the case, since this improper integral does not evaluate a finite fixed real number, like my previous one did, then I will say that this particular improper integral diverges. Whereas in my previous example, it converges. If you want me to be concrete with my definition, I'll say this. If an improper integral evaluates to a finite fixed real number, it converges. If it doesn't, then it diverges. Yes?
So, can we say that the square root of infinity is infinity?
Yeah. Yes.
We can't.
Yeah. Yeah, that's what really annoyed me. There's a commercial out. Have you guys seen the commercial with the...
Yeah, you were talking about
Did I
that
mention
before.
that? Oh my gosh, that's so good.
Can you show it like visually, like?
Yes. So you guys mind? Watch my trickery. I'm serious. Because I didn't unitize my axes, I think the curve looks, roughly speaking, like y equals 1 over x squared. It's just curved a bit different. And it's a bit different in the way that as x increases, my y values weren't increasing quite as rapidly as they did before with y equals 1 over x squared, which means I grab more and more areas that go out. Even though to the naked eye it looks closely to be the same as my previous example, the curvature is not the same. And I get an unbounded region that is infinite area. It's sort of like saying this. You know, walking on the x-axis further and further, and I got this bag with a hole in it tied around my belt. And I'm going out on the x-axis, putting more and more in my bag. In the first example, it's like I can walk all the way out as far as I want, and I never fill the bag up. But with my second example, I'm walking out and putting more and more in my bag until it overflows, and I can't contain the value that represents the area. So, do you guys mind if I jump to number 3? Yes.
So, I don't quite understand how the first one is 1, but that one just keeps going.
Because I think with y equals 1 over x squared, as x gets large, y is getting close to 0 fast enough for this unbounded region to have finite area. And you look at me like that. I think with my second example, my y values are still getting to 0 as x increases up now, or approaching 0. It's just they're not going to 0 fast enough to give me a finite area underneath the curve. That's what's so interesting about these improper integrals. Sometimes those bounded regions have finite area, sometimes not. I want you to hold the thought just for a minute. So my example number 3. Oh shoot, there isn't one. It wasn't meant to be. So, I want you guys to deal with this particular question. By the way, this is not pertinent merely to what we're discussing in this chapter. This becomes very important in the next couple weeks.
Is that a P?
That is a P, yes.
Okay.
So let me hide the integral. By the way, Brad, I didn't put the bound, sorry. I meant that. Let's evaluate this improper integral and ascertain for what values of P it converges and for what values of P it diverges. No matter what P is, I think I have to re-represent this as the limit of a proper integral.
So is P a constant or is it a variable?
P is a constant, it remains fixed. You know it's a
Okay.
constant because my variable of integration is x. It's the only variable in question.
Okay.
But since I don't know what P is, my question is pertinent. For what values of P does this integral converge? For what values does it diverge?
So why does it change to PP?
It changed to what? What did you say it changed to? Sorry. My apologies. And I got P's in my mind. I think in anti-differentiating, no tricks here, everybody. Piece of cake truly is. I said piece of cake, cheaters.
X to the P or 1 minus P
Yeah, is that
over
okay?
1 minus P.
I'm tired too. Just double check our road we took. Or shall I say, since P is just a constant, has nothing to do with T, I'll pull it out. And I've got the limit as t plays its game of, I got an idea, this antiderivative evaluated the upper bound of integration. Minus this antiderivative evaluated the lower bound of integration. And now let's talk about this limit. So everybody, if p is strictly less than 1, don't you guys agree this exponent is strictly negative? But if it's strictly negative, doesn't that take this t to the negative power, throw it upstairs, and I get t to a positive power? But clearly that's going to diverge. If t is being raised to a positive power upstairs, as t increases that bound, clearly this interval diverges. You guys stop me if I'm being unclear. If p is strictly bigger than 1, let's see what happens. If p is strictly bigger than 1, here's what's going to happen, I think. This exponent is positive. So t to a positive power stays downstairs. But as t increases that bound, t to a positive power increases that bound. But 1 divided by something that's increasing with that bound tends to 0. And so I think in evaluating this limit, this term goes to 0. What's left over is nothing more than negative 1. Oh, shoot, I forgot a coefficient out front. So this thing times negative 1 is just 1 over p minus 1. So I converge, and I converge to 1 over p minus 1. You guys, so far so good? Next. Oh, I missed something, didn't I? Shoot. Look what I missed, you guys. So can we just slam it in real quick? Plugging 1 in for p, I get. Who cares? Because out front, my coefficient is undefined. And so I guess what I'm doing on the board doesn't apply. Shoot. That means I got to look at a whole new special case scenario. Let's do it. If p is equal to 1, let's see what happens when I evaluate this interval. I think it's a special case scenario. I think by definition I get this limit. I think an anti-differentiated 1 over x, life is a 100% absolute piece of cake. Meaning I'm going to evaluate this limit. Actually, I misspoke. Maybe you can evaluate this limit. What do you get? Yeah, I agree. So I think clearly this improper integral diverges as well. So can I restate all this? I think this improper integral right here only converges if p is strictly bigger than positive 1. So last time in class, you and I saw that when I looked at the integral with 1 over x inside there, it really did diverge. I just proved it.
So you said this becomes useful later in the course. How is it applied later in the course?
You know, for those of you in this room who've seen this material before, we've covered a concept called series. You know, a lot of times with the series, which by the way is a fancy word for a big sum, if I have a sum in this form right here, it's an infinite series. And I maintain for some values of p, the series converges, which gives me a finite fixed real number. And for some series, even though they're infinite series, it diverges. And with a lot of series, well, not all, but some series, I can give up looking at the evaluation of this infinite series and look at the corresponding improper integral, and it can tell me whether or not the series converges or diverges if certain conditions are being met. And so it's really going to be what I refer to as one of my tests for convergence for infinite series, whether converge or diverge. Again, I know some of you coming in, you've seen this material before. I'm really referring to a p series. That's what I'm referring to. Well, just give me a few days, we'll get there. I promise.
Is that like power series, or is that
It's
something
just
different?
right before I discuss power series.
Okay.
Oh, Well, I guess I should have just stopped again, you guys. Look, if I ask you this question on the exam, are you gonna rewrite this as a limit of an improper interval? Yes or no? Yeah, let's just write p equals 1 because 1 over p minus 1 is 1 over 2 minus 1, which is 1. Piece of cake. What can you say about 1 over p minus 1 here? Say it again. Yeah, how about saying nothing in the sense that, you know, if p is not bigger than 1, I don't use that formula. My particular series diverges. What about this question? Yes or no? Can you give me an answer?
Yes.
Yeah, piece of cake, because p is understood to be 3/2, and so I think this is just going to be 1 over my p-value minus 1, or shall I say 1 over 1/2, or shall I say just positive 2? True, piece of cake, isn't it?
But where's the p-value on that?
The p-value is here. I think x to the first times x to the 1/2
Yeah,
is x to the sum of those two exponents.
so
1/2,
3/2, right?
which is just 3/2.
Okay,
That's why I'm saying my p-value is understood to be 3/2.
okay.
Ooh, what about my next question? Number 4. Okay, you guys, I confess this looks more complex, but technically speaking, what's really going on is that since I have non-finite values both at the upper and lower bound of integration, here's what I get to do. Just like you did back in Math 30, I have the opportunity, no tricks, and to rewrite it as one interval, as the sum of these two. First, A is any real number I darn well please. Can I choose more selectively? I'm tired. I'm beating the clock. I'm in front of class making silly arithmetic errors. I'll choose this specific A value because it's easy to deal with. But I think that merely gives me the limit as t
Approaches negative infinity,
of the proper interval from
t to negative infinity,
t to 0
or 0.
in the
Oh, yeah,
first
0.
case of this mess in X. Likewise over here, as with my previous examples, I'll rewrite this limit. Yes.
Where you start the limit, do you have to specify that it's coming from the left or the right?
I never do if t increases or decreases that bound for this reason. If t is going to behave in this fashion, I can't come into negative infinity from the left-hand side. So I can't even think of this as in that fashion. This is for free, even though there's no superscripts here. This is for free at one side of the limit. Because I can only go to negative infinity from the right direction. Same thing over here, but reverse directions. And keep something else in mind, you guys. Watch. These are proper intervals for which this function is continuous over that interval. So up here, better be the case that this interval is continuous everywhere within, or I've got issues that I have to deal with in a few minutes. I'll have to take care of. Next. Well, I think for free, you guys, I can evaluate this integral off the top of my head. I get nothing more than top of my head, very top.
Inverse tangent.
Inverse tangent. Same thing over here. And I can evaluate. What can you say about the inverse tangent of t as t does this? Negative pi over 2. Oh, but shoot, that's the second term since that's my lower bound of integration, so I guess I get inverse tangent of 0 minus it. I'll add to that the evaluation of this particular limit, but the inverse tangent of t as t plays this game goes to minus the inverse tangent of add lower bound of integration. But that merely is gonna give me, wow, we computed the exact area underneath that curve, y equals 1 over 1 plus x squared, and you know what that looks like. Sort of like that bell-shaped curve, isn't it?
How did you get pi over 2 for inverse tangent t?
In my head, I was graphing this equation. Yes? No? Please, no silence.
I just thought of it as tangent, you do tangent of.
Okay, yeah, don't listen to me. Do this instead. X-axis, y-axis. Y equals a tangent of x. Well, at least one full cycle looks like this. With vertical asymptotes at x equals plus or minus pi halves, that's one cycle of it. Restrict its domain to that one cycle, and reflect through the line y equals x, and you got the graph of this inverse function, which is right there.
So where does the t come in?
Well, I made that letter up out of thin air, because I wanted to, I don't know, allow this upper bound to be finite fixed. That's not the same thing as infinity. So if I'm going to replace this infinity with a t, I better take the limit of this interval as t increases that bound. Think of this sort of as my new technique for giving you a technique for evaluating these improper integrals.
Okay, I see.
Well, if that is okay, so good old happy times
Yeah.
of the past.
Fun.
You like that?
Oh, no, I did a bunch of these last night.
No,
They're really
you guys, I don't like it. No, it works. Sorry. I had a sign change in my head. Would you guys agree, roughly speaking, I'm not being careful? That in the right-hand plane, from 1 on out, curve is decreasing. Its y value is approaching 0. Sort of like my last graph, something like that. I know I'm being very restrictive. I know in the left-hand plane I get vertical asymptotes. I know the y-axis is acting as a vertical asymptote as well. I just don't care because I'm restricting my attention to x values of 1 and on up. And I think here's the boundary region. And if I were to rotate that about the horizontal x-axis, would you guys not agree that this method is appropriate? And if the disk method is appropriate, I'd probably be considering these vertical rectangles like this. But cheaper is when I resolve that about the horizontal x-axis, I get disks that look like this. And in setting up my integral, I think the volume is going to be nothing more than the integral from 1 on up of pi, I'll pull it out if you don't mind, times my radius squared. But I'm integrating with respect to what variable?
X.
I agree with that. Now, as far as the radius of this disk is concerned, if I consider an arbitrary point on the outer edge, x sub I comma y sub I, don't you guys agree the radius is just y sub I? So when I take the limit of a Riemann sum, I end up generating just simply a y value, but in terms of x, I guess that's given by my 1 over x plus x squared. Ah, shoot. I meant to say this. That being the case, I'm now left with pi times the limit as t increases without bound of the integral from 1 to t of my 1 over x plus x squared twice. So, you guys, I get to stall for a minute. Honestly, how do you evaluate that integral? You experts of chapter 7. I use the word expert.
No, I do, yeah.
I like that. I think we're dealing with partial fraction decomposition because I think we're sitting in front of us. Is this integral? So if I were to pull out my nifty piece of scratch paper, I'd probably take this one fraction here. Guys, I'm talking again too much. Again, you're the experts. What do I get?
So that equal to a times,
A over.
or a over x squared. Oh yeah, plus b over x squared, plus cx plus d. Oh no.
That would
Yes.
work. That would work.
If you foiled it out,
Look at this. Yeah, right.
yeah.
If you foil it out, you're
yeah,
it's fine.
or you could do that. Yeah.
Plus d over 1 plus x squared.
There, nice. That being the case, I think 1 is equal to a times x times 1 plus x twice, plus b times 1 plus x twice, plus c times x twice times 1 factor 1 plus x, and finally plus d times x twice. And I maintain, if x is equal to 0, or if x is equal to -1, oh, nice piece of cake. If x is equal to 0, I see that, what do I see? That b is equal to 1. You guys tell me if I'm messing up my arithmetic. If x is equal to -1, however, I think that suggests that d is equal to +1. Ah, shoot, you guys, now I'm running out of gas. I gotta slow down and see what the heck I could do to generate some other constants. I got an idea. Let's look at the coefficients of x cubed. Here it is on the left-hand side. Here it is on the right-hand side. Oh, but shoot, I have neither A nor C. I guess I better build another equation. Any suggestions? Will be something relatively convenient. You're right, constant would be really nice. Unfortunately, I just did it in my head, and I get exactly that again. It just tells me something about B. You got me? What else do you want to do? You want to look at x squared terms. I'll do that. On the left-hand side, easy. On the right-hand side, I got to slow down. On the right-hand side, notice how the middle term, if I expand it, is a 2x. When I distribute it, that means the coefficient of x squared is 2a. Next. In here, if I expand out the x squared term, it's just actually x squared times a b, which is just this. And here, when I expand out, sorry, there's no expansion, is there? There's my constant term. With that distributed, it becomes an x squared term, whose coefficient is this. And lastly, oh, there's only one term here, and it is an x squared term. So I guess the coefficient is d. This tells me that 2a plus c is equal to -2. But from this equation, I know that a plus c is equal to 0. So if I subtract one equation from the other, doesn't it tell me that a is equal to, is that -2? But if a is equal to -2, and a plus c is equal to 0, it suggests that c is equal to +2. You guys can double check my arithmetic.
Are you subtracting the top and the bottom?
I am.
A minus 2a is negative. Okay.
Is that better?
Yeah.
Like I said, just double check my arithmetic. I guess that means in the end, that what's sitting in front of me is nothing more than pi times the limit as t plays its game. A big mess. But I think the mess ends up being specifically this. You guys, I can't keep looking. What's A? What's B?
1,
And what's C?
2,
And D?
1.
Oh,
Shouldn't
sorry.
D be squared
Did
at
I
the
miss
bottom?
parentheses? Oh, thank you. I missed my squaring as well. My goodness. You guys, I'm running out of room. Can I cheat? Come in here. And if I do, that's going to give me pi times the limit as t plays its game. Let's anti-differentiate. Let's do the anti-differentiate.
Negative 2 times natural log of x minus 1 over x.
Very good.
Plus 2 times natural log of x plus 1.
I know I should have absolute values, but you guys, x is only going to range from 1 on up, so I know everything out there is going to be positive.
Minus 1 over x plus 1. No, it shouldn't be squared.
My apologies, thank you very much. I wasn't the anti-differential. And I'm going to value it from here to here. But I think this gives me pi times the limit as t plays its game. Evaluating up my upper bound of integration, I don't know, you guys. What does that give me? Does that give me 2 natural log of this ratio? Minus this fraction, minus this fraction. But now when I subtract off of this, these 3 terms of value at the lower bound of integration, does that give me a negative 1 plus 2 natural log of 2? Minus 1/2. If you guys have double checked my arithmetic. Now I gotta confess, life's not that bad. Because technically speaking, as I evaluate this limit as t plays this game, look at these fractions. These 2 fractions, they do what? At those extreme values of t.
About 0.
What about this? I heard that. Did you guys see why? When I take the limit of the natural log of stuff, since over this interval from 1 on up, the natural log function is continuous, I can now take the limit of the input function. Now when you take the limit of this, as t increases that bound, you get positive 1. But the limit of some mess going to positive 1 is just simply going to be 0. And so I think in the end, with the evaluation of my limit, look at this. I'm simply left with 2. I misspoke. I meant negative 2, natural log of 2. Yikes. Plus 3/2. Now I'm getting slow with my arithmetic. I just didn't want to end this discussion without a non-trivial example.
It's not the most fun by pi, right?
Thank you very much. I appreciate that. I agree.
So for these ones, would this be an exam question or expected to know?
Oh, I think this would be a really nice exam question. Emphatically, because it means I get to test you again on your integration techniques, and I get to loop back and make sure you're reviewing for the final exam when it comes to volumes and solids and regulation. Which I really should have done the last exam. This last exam, you guys just learned how to integrate. I was really concentrating on integration techniques. You know what, you guys? And this next example, I really do think this is another example of an improper integral, but for a different reason than before. So far, I've looked at improper integrals where one of my bounds of integration was not finite, or at least one was not finite. Here, I would still classify this as an improper integral, simply because in terms of my area interpretation of it, when I look underneath this graph right here, as x ranging from 0 to 1, I maintain it's an unbounded region. And because the integrand gives me an unbounded region over this integral, I will subclassify this as improper integral, but just for that different reason. And my way to deal with it is this easy.
Why wouldn't it be 2 to 1?
Say it again.
Why wouldn't it be 2 to 1?
What do you mean?
Well, because it
is.
can't be 0. Oh, okay. I just wasn't seeing things right.
I'll stay away. And I maintain life is piece of cake. Now I'm serious, no tricks. I really can deal with this particular proper integral within the limit. And so anti-differentiate what you see in the integrand position. I'm going to be left with this. Evaluate it from here to here. But I think that gives me the following. That's the limit as t plays this game. Of, yikes, what does that give me? Does that give me a positive 1 minus 1 over t? So you guys, relax and take a peek at that and tell me what the heck happens with this algebraic expression as t approaches 0 from the right-hand side. It diverges. That being the case, my original integral diverges as well. Oh, that was so much fun. Let's do it again.
A question about these really fast.
Yes, please. Shoot.
So, when we learned how to do limits last semester, often we would try points that were really close to, like, say, 0. Like, if it's coming from the right, it would be like 0.0001 or something like that.
Yeah.
In the book, they find exact answers, and I don't really know how they're getting the exact answers. Because I would just come
Oh.
up with a decimal.
You mean with this type of improper integral?
Well, with some of these, I don't know if this one really works out like that, but some of these, you just come up with a decimal
answer. Address that issue
answer.
with this example because it diverges.
Yeah.
So maybe my next example, I'll make one up that
Okay.
converges, and I'll show you how to get the exact value. Because I do want you to get the exact value.
Okay.
So what number am I on? 8? Number 8?
Yep.
You guys, what number am I on? No, I think I'm on 7. I
Yeah.
think I'm completely wrong. Here's why. I fully understand that we trained you to think in the following fashion back in Math 30. X-axis, Y-axis. Got some curve, that's an odd function. And I'm integrated from negative a to positive a. I have to confess, if f is an odd function, then the evaluation of def integral using the language of Math 30 really has to be this. Because the positive area on the right-hand side cancels with the negative area on the left-hand side, and I'm dealing with a lot of symmetry. But you have to confess, that was Math 30, where this function was continuous over the interval from negative a to a. And if you look at this picture right here, it's not so pretty, because I'm not continuous over the interval from negative 1 to positive 1. So I can't use these old tricks from Math 30. As a matter of fact, I maintain it's not 0. Even though you can sit